Okay, lesson 3, rates of change in linear and quadratic functions. So we're going to find the average rates of change over a closed interval. We're going to find the slope of the secant line over a closed interval. We're going to use average rates of change to determine concavity. And we're going to write a linear equation for consecutive equal length input intervals that represent the average rate of change of a quadratic function. So in the previous lesson, we looked at the rates of change for multiple representations, including graphs, equations, tables, and verbal descriptions. In this lesson, we want to consider rates of change in linear and quadratic functions. So we can see here it says that the average rate of change in the secant line. A secant line is a line joining 2 points on a function. Now that's different than that tangent line that we talked about in the previous lesson. The tangent line, remember, just touched 1 point and was always on the outside of the graph, where the secant line is going to join 2 points on the function, and it can go onto the inside of the graph if it needs to. All right, so finding the slope of the secant line through 2 points will give you the average rate of change over the interval, over the closed interval that includes those x values. You have known how to do this since your first algebra class. We just have new notation. And so we did use this notation in the other lesson. So the average rate of change of f on the closed interval from a to b, remember our average rate of change is just our slope. So it's our change in our y's over our change in the x, which is equal to the slope, and they put subscript sec, meaning the slope of the secant, which is equal to the function evaluated at point B when x is b minus the function evaluated when x is a, all over b minus a. So remember that f of b is like your y2 and f of a is like your y1. So it's still the same formula, it's just in function notation. All right, example 1. So let's consider the graph at the right. It passes through the point 0, -3, and 4, 3. Explain how you know its equation is y equals 3/2 x minus 3. And so we can look at the points here. So it told us it's at 0, -3, and it's at 4, 3. Even if they didn't tell us, we could find those. And so first off is we know that our slope of that linear function is going to be 3/2 because we can do our rise over run. So because the slope is equal to the change in the y's over the change in the x, which is equal to 3/2. That's our m. Okay, and then our y-intercept, which remember is where it crosses the y-axis, that's our b value, and we can see it crosses at -3. So therefore, if we use y equals mx plus b for our linear line, then we know that y is equal to 3/2 x minus 3 is the equation. All right, B says, what do you notice about the average rate of change for a linear function? So it doesn't matter what points we pick here. If we pick the 2 there, let me change colors. Or if I picked this one, I'll do an X, and this point, any 2 points there, we'll notice that that rate of change, that average rate of change, is still going to be the same. So it's going to be constant. No matter what 2 points we pick, the rate of change is still going to be 3/2. All right, C says, how is the average rate of change related to the equation itself? All right, so how's the average rate of change related to the equation itself? So we know that our average rate of change is equal to 3/2, and since we know that's equal to the change in the y over the change in the x, so for every change in x, and I'm thinking about it as a whole number change, okay? So every change in x, and as x increases there, the y value increases by 3/2. Now we could have put, like, for every time x increases by 2, the y value increases by 3, since it is 3/2. But remember that 3/2 is also the same as 3/2 over 1. So that's why we said for every change in x, that's our x's down there, the y value is going to increase by 3/2. All right, D says use a grid at the right to sketch a graph of a function that represents the average rate of change of the linear function. Hint, consider your answer to part B. All right, so we had said that our average rate of change was equal to 3/2, which is the same as 1.5. We also said then that in B, we had said that the average rate of change for a linear function is going to be constant. So we know in a constant equation, it's just y equals a number. So it's just going to be y equals our average rate of change. So we'll go to 1.5 here, and we're going to draw our constant line. I can do better than that. All right, example 2. It says, given the quadratic function, f of x equals x squared minus 6x plus 5. Graph at the right says use the table of values to find the average rates of change on consecutive equal length intervals of x values. Record your results in the table. All right, so we would go through and calculate the average rate of change between when x is 0 and 1, when x is 1 and 2, between when x is 2 and 3, 3 and 4, 4 and 5, 5 and 6. All right, and we need to make sure, because these are nice, pretty numbers, that we can do this without necessarily using our calculator, okay? It's very likely to be a non-calculator question. So when we go through and we do so for this first one, we would do f of 1 minus f of 0 over 1 minus 0. We can see f of 1 is 0 minus f of 0, which is 5, over 1 minus 0, which is 1, so we end up with negative 5. Okay, and we would keep doing the same thing, and we'll find between 1 and 2, that's negative 3, then it's negative 1, 1, 3, and 5. All right, now I believe your table has an additional line here, because then they're saying, hey, let's look at, let me go back and find it. Give me 1 second here, because I know when I was going over it earlier, my notes had it, but these didn't. Yeah, so yours has a change in the average rate of change down here. Okay, and so what it is you're looking at these, what they call second differences. Okay, and so if you look at how far is it from negative 5 to negative 3, we're increasing by 2. Negative 3 to negative 1 is by 2. Negative 1 to 1. And so what we see there is the change in those average rate of changes is constant. And because it's called the second differences, that's why it's a quadratic. So it says, using the results from the table of average rates of change, do you notice a pattern in these rates of change? And so that's what we just did there. So we looked and we saw that the change in the average rates of change were each increasing by 2. What can you say about the rate of change at x equals 3 and explain? All right, so as our intervals move to the right, the rates increase by a factor of 2. So that's going to answer the first part there. So as our intervals move to the right, the rates increase by 2. All right, so then at x equals 3, so it said there, what can you say about the rate of change at x equals 3 and explain? So at x equals 3, we're down here. And so remember, that's a minimum point, or we can say it's a turning point. That way the turning point will cover a minimum or a maximum, okay? And so we talked about a turning point or a minimum point. That is the only point in which we can actually find the average rate of change. Because remember, we use that tangent line right there, and so we know that its slope is 0. So at x equals 3, the function has a turning point. and the rate of change is 0. Remember, anywhere we have a maximum or minimum point, the rate of change there, the average rate of change is going to be 0 at that point. That is the only point that we can actually tell you what the average rate of change is. Remember, otherwise we said we have to look at small intervals. All right, so 3 essential facts. Over any length input value interval, the average rate of change for a linear function is, and we said this earlier, it's going to be constant. If it's a linear function, the average rate of change is going to be constant. Given consecutive equal length input value intervals, the average rate of change of a quadratic function can be given by a linear function. And we kind of just saw that because we saw those second differences. It was increasing by 2, which would be the slope of the average rate of change. All right. Then the average rate of change over the closed interval from A to B is the slope of the secant line. So it's going to be the slope of the line when we that connects the 2 points that we're looking at. All right, average rate of change and concavity. So we've talked about both of these so far. So example 3 says in a quadratic function, we can determine the curvature or concavity of the graph by considering the average rate of change over equal length x intervals. Sketch secant lines on the graph shown below. All right, and this one is supposed to say tangent, not secant lines. Just remember the tangent line is where it touches it in that one spot, okay? And so I'm trying really hard just to hit that one spot there. And so on the first one here, I drew in my tangent lines. I can see that my slope is increasing. Be careful because even at this point, I know the slope is going down, but it's increasing because the previous slope would have been steeper. And since this one's not as steep, it's changing from that really steep negative slope to a less steep negative slope, which means the slope of the number itself is getting bigger, so therefore it is increasing. It might have been like a negative 1/2 here, where this would be a negative 1/4. Even though it's still, the slope itself is decreasing, when you're dealing with a concavity, the slope is starting to increase from the previous one. All right. And then concave down, and drawing our little tangent lines here. That's not a good one. That one didn't even hit. Okay, and on this one we can see that the slope is decreasing. So my slope is getting smaller and smaller. And be careful, that gets a little confusing because on this side you're like, no, my slope is positive. It is positive, but from the previous point, that line right there is not as steep as this line right here. So therefore, it's starting to decrease. All right, example 4. It says, using the function from example 2, let's consider what the graph of the average rate of change for this quadratic function would look like. So the parabola is concave up because the average rate of change on the equal length interval is increasing. So this is the one where we did the second differences, where we saw that the differences was 2 in each one. And so we saw that the first between 1 and 2, hold on, what were the numbers? Between x is 0 and 1, we said our average rate of change was -5. Between 1 and 2, our average rate of change was -3. Between 2 and 3, our average rate of change was -1. So our average rate of change is increasing. Okay, and that's by a factor of 2. So let's call this the slope of the new function. We also observed that the quadratic function changes from decreasing to increasing at the vertex, which was where the x equaled 3. So the rate there is 0. Remember, our rate of change at that vertex or at that turning point is 0. All right, we say that the slope is constant at that point. You can also use the ordered pair, your x value, comma, your rate of change for a point on the graph. So C says, using your results from parts A and B, write an equation for a linear equation to represent the average rate of change of the quadratic function. Graph the equation on the grid provided. All right, so we know that our slope was equal to 2. And we also know an ordered pair on there because they said we could use x, comma, the rate of change at that point, okay? So our ordered pair there then would be the x that was 3 and its rate, which is 0. And so we know it's going to be linear, so we know it's y equals mx plus b. So we can plug in, remember this is an x and a y, so we know 0 equals, we know our m is 2, our x is 3, plus b. So 0 equals 6 plus b, solve for b. And so we get negative 6 equals b. So therefore we know that the the equation of linear equation to represent the average rate of change of the quadratic function is y equals 2x minus 6. All right, and then if we want to see this graphed, we know that using our equation, we know our y-intercept is down here at negative 6, and our slope is 2. And you can see right there is that 3, 0, which we said was going to be on there. And we can draw our line from there. All right, in example 5, it says, let's generalize the procedure for finding the average rate of change or velocity to any function over an interval. So A says, let f of x equal x squared plus 2, find the average rate of change from t equals 2 to t equals 4. All right, so, oops, let me turn my pen back on. All right, so we know that our x1, which is our t1, is 2. And so f of t1, well, let me do this. So then I know that my y1 is going to be f of t1, which is f of 2. And so it gives me 2 squared plus 2, which is 6. We know x2, which is our t2, is 4. And so y2 is f of t2, because I'm going to start changing this more to function notation, so that's why I'm kind of writing it out here. So we're looking at f of 4, which is 4 squared plus 2, which is 18. And then my average rate of change is going to be my f of 4 minus my f of 2 all over 4 minus 2. So 18 minus 6 over 2, which is 12 over 2, which is, thinking ahead, which is 6. All right, B says let f of x equal x squared plus 2. Find the average rate of change from t equals 2 to t equals 2 plus h. All right, so x1, t1, which is 2, and so we just work that one out. We knew it was 6. Now remember on this next one, we're plugging in that 2 plus h, but I'm plugging in something with an h, so I'm going to get an answer with an h. We're not just plugging in a number. When you plug in a number, you usually get a number answer. When you plug in something with a variable, you're going to get a variable in the answer, okay? So we end up with 2 plus h squared plus 2. We're going to do FOIL here, 2 plus h times 2 plus h. and then we have our plus 2. So we do that, we'll get 4 plus 4h, when I combine those like terms, plus h squared plus 2. So 6 plus 4h plus h squared. Then we're going to go through and do our average rate of change. So it's going to be our f of 2 plus h minus our f of 2 all over 2 plus h minus 2. This is 6 plus 4h plus h squared minus f of 2 was 6 all over, and here these 2's will cancel, so I just get h. My 6's cancel, so I get 4h plus h squared all over h. And then remember, because all 3 of these have an h, we can greatest common factor it out. So I'm going to take an h out of each of these, which ends up giving us 4, because the h in it disappears, plus h squared. Take out an h is h all over 1. Oops, but I don't have to put the all over 1. So be careful, my answer is hiding. It's right there. Then C says, write a general formula for the average rate of change or the difference quotient for any 2 points, A, f of A, and A plus H, comma, f of A plus H. So just using our average rate of change formula, we know it's going to be f of A plus H minus f of A all over A plus H minus A. And we can simplify the denominator there. So we got our f of A plus H minus f of A all over, the a's will cancel, and so we just get h, which is what they call the difference quotient. All right, and that is the end of the first part of lesson 3.